Welcome to this explainer. Today, we're unpacking the rigorous API Specification 5L to uncover the hidden engineering that keeps line pipes from failing. We're talking about the critical steel arteries powering our modern world, stretching across continents and diving into the deepest oceans. But they don't just survive out there by accident. There is a meticulously detailed blueprint keeping them intact. So it brings up a massive question, right? How exactly do these steel arteries survive the most punishing, corrosive, and high-pressure environments on Earth without catastrophic failure? Think about it. When millions of barrels of product are flowing under immense pressure, a single microscopic flaw? That's an absolute disaster waiting to happen. The secret to avoiding that lies in API Specification 5L. It's a document that literally leaves zero room for guesswork. All right, let's dive into this spec. We're going to cover testing for extreme environments, how to decode those complex pipe markings, through flow line specs, offshore requirements, and finally, quality control and tolerances. Starting off with Part 1, testing for extreme environments, specifically looking at Annex H, which deals with sour service. Now, when pipes transport sour gas, the chemical attack they face is just relentless. Our main enemies here are hydrogen-induced cracking and sulfide stress cracking. To fight this off, these grueling 720-hour tests are absolutely mandatory. Just imagine putting stress steel into a bath saturated with chemically pure hydrogen sulfide for 30 days straight. It's intense, but it ensures hydrogen atoms don't blister the steel and snap the pipe under pressure. Take a look at the tiny X marks across these weld cross-sections here. They mark exactly where Vickers hardness tests have to happen. Why does this matter? Well, if a specific zone is too hard, it actually becomes brittle and way more susceptible to cracking in those sour environments. So hardness cannot exceed strict limits, and the testing has to hit the parent metal, the heat-affected zone, and dead center on the weld itself. And for high-frequency welded, or HFW pipes, the testing grid expands even further. They have to maintain a really strict 1.5 millimeter distance from the fusion line, checking just 1/10 of an inch from the surface, and spacing those indentations precisely 1 millimeter apart. This kind of microscopic scrutiny is there to guarantee the welding process hasn't accidentally created a brittle Achilles heel. Moving on to Part 2, decoding API pipe markings, or basically knowing your sour class. Out in the field, you have to know a pipe's armor at a glance. Those sour class designers, Class A, L, and F, tell us exactly which test solutions the pipe actually survived. For instance, if you see X52 MSA, that S proudly declares it's fit for sour service, and the A means it passed some incredibly severe testing. C and O, that means it's rated for offshore use. Basically, this standardized alphabet soup is a critical safety lifeline for engineers. Let's hit Part 3. Through flowline pipe specs, which covers Annex I and TFL requirements. So in modern operations, maintenance tools are often pumped physically through the pipe itself. To guarantee these tools don't get snagged, through flowline or TFL pipes face this brutal 3-step drift test. They literally pass a large, precision-machined metal cylinder called a drift mandrel through the entire 40-foot pipe while making sure there's absolutely no sagging. If that cylinder catches for even a microsecond, the pipe fails, no exceptions. And the dimensions of this mandrel? Incredibly unforgiving. If a pipe has an inside diameter of D, the mandrel is D minus just 2.4 or 3.2 millimeters. That is an astonishingly tight clearance for heavy industrial steel. It proves that the internal geometry has to be manufactured to near absolute perfection. Now for Part 4, offshore service requirements. This is Annex J, all about surviving the seafloor. Laying pipe in deep water subjects the steel to immense bending stresses and crushing hydrostatic pressures. To survive this, Annex J demands a massive escalation in testing. Standard visual checks? Tossed out. Instead, they require comprehensive, full-body ultrasonic and magnetic particle inspections. What they're doing is actively hunting for microscopic laminations inside the steel that could pull apart when bent on a laying vessel. Check out how strictly carbon equivalents and elements like titanium are controlled here. We aren't just melting down random scrap metal. A high carbon equivalent makes steel harder, sure, but it also makes it much harder to weld successfully out on a pitching ocean barge. By capping these elements, we ensure the steel remains incredibly tough, yet ductile enough to work with. Also, notice the rigid caps on yield strength. Standard grades often just care about hitting a minimum strength, but offshore demands a strict maximum too. Think about it.
If a pipe is unexpectedly overstrong, it won't bend properly around the reeling ship during installation, which can lead to sudden, catastrophic snapping. In this environment, predictability is just as vital as raw strength. Bringing us to our final section, Part 5, Quality Control and Tolerances, or what we call the margins of safety.
To consistently manufacture tens of thousands of miles of perfect pipe, the physical out-of-roundness tolerances have to be microscopic. For many offshore pipes, the deviation at the pipe end cannot exceed 1.6 millimeters. When you're welding two massive pipes together on a pitching barge in the North Sea, if the ends aren't perfectly circular, the welds simply won't align. And an imperfect weld, that is exactly where a pipeline bursts.
This relentless quality control means mandatory tensile and impact testing for every single batch. A factory can't just test the first pipe of the day and hope the rest turn out okay. Depending on the diameter, 1 in every 50 or 100 pipes is pulled off the line and physically destroyed in testing. This crazy high frequency guarantees that even the slightest drift in manufacturing is caught immediately.
But as this vital warning from the specification reminds us, simply passing a baseline stress test doesn't automatically mean the pipe is invincible. This is a super crucial note from Annex H. The engineers writing this code are explicitly stating, don't get complacent. Just because your pipe survived a baseline WAB test at 72% of its yield strength doesn't mean it's ready for the most unpredictable, severe, sour regions. It's there to push engineers to constantly evaluate the specific real-world exposure they'll face, rather than just blindly checking a box on a form. So, knowing all the grueling tests and microscopic tolerances we've covered in this explainer, it leaves you wondering, how heavily does our entire modern world rely on the unseen perfection of these steel cylinders? Next time you turn on a heater, think about the thousands of miles of certified steel buried beneath us, passing microscopic inspections to hold back the ocean and resist toxic gas. If a 2-millimeter deviation spells disaster, what other invisible engineering miracles are keeping our world spinning right now?